Okay. Usually comes together at the end. Was that
We're still going to upload the video from last Tuesday.
from last Tuesday or from this past Tuesday?
Past Tuesday.
Oh, yeah. I have the file. Oh, I forgot to upload it. So I'll do it. I'll do it today.
Thank you.
Yeah. What's up? Usually not. No.
It's either old or really high. It's never. I feel cold. I never.
Time. Yeah, I'll do that.
Yeah. Getting a copy from the science. Why never stop this? That I can. I genuinely. To this day, I don't have much. Yeah, you know, yeah, I think this is things like, honestly, I feel like if I get a sticker with that, it's like.
Yeah, that'd be kind of hard.
It would be tough.
You gotta have a screen reader all the way up.
Yeah, yeah.
You scare the shit out of somebody.
Yeah, you guys, I'm just listening to you guys.
You heard me?
Yeah,
We basically did this problem. I didn't want to make somebody.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. For the last time, how's everyone doing today? Good, hanging in there. I know it's almost finals week. Okay, all right. So today, no new information today. Today is just going to be a review session. So I looked at the poll. 10 minutes ago, and these were the top two topics that were on the poll. So the most requested topic was radiation exchange. So that's kind of the stuff that we've been doing last couple of weeks. So what I thought I would do for that one is I would just kind of review some core concepts and then go over the solution to the practice final problem that I've posted. So just so you can kind of see how that's my logic behind that. Okay. And then the second most popular one was 1D radial conduction. So that's basically going back all the way back to our first midterm, basically conduction in radial systems, cylindrical systems and spherical systems. So we'll cover that kind of in the second half of today. Okay. All right, so just a reminder for everyone. So after today, the next time I will see most of you is going to be next Tuesday for the final exam. I will have office hours next week. So actually, let me write that down right now. Okay. So for you guys, the only relevant office hours is going to be Monday because that's the last office hours. That's going to be for the exam. I'll have office hours after that, but I mean, if you guys want to come by and say hi, that's fine too. But Monday, I'm going to have office hours at my normal time, so that's going to be from 10 a.m. to 11 a.m. Okay. And so that will be over Zoom, just like normal. Okay. And so if you have any last minute questions on the study guides or the practice problems, you can come by at that time. I'm gonna have extra office hours on Monday too, also on Zoom. This one's gonna be in the afternoon. So this will be 3 p.m. to 4 p.m. All right, and so if you can't make it to the morning one, like maybe you have a final exam during that time, I opened up a second one for you as well. Okay, so if you have last minute questions, don't be afraid to come by. Those two office hour sessions on Monday, and then Tuesday we'll take the exam. Okay. All right. Any questions about anything before we get started for today? Solutions for homework 7. I am going to post that tonight. Or it's due tonight. So maybe I'll post it tomorrow night, just so that you'll have that for your studying as well. Okay. All right. So let's go ahead and get started. Okay. So first topic, the most requested one, question from the chat. Is there any specific question that you recommend studying? Well, so I've been telling people that the radiation exchange problem that's going to be on the exam, pretty similar to the example that we did on Tuesday. So I would definitely look at that one. The other ones are going to be more kind of hybrid questions. And so I would just kind of, definitely look at the practice exam, definitely look at all the homework we've done, all the examples we've done in class, and go from there. Lump capacitance will not be on the final. So transient conduction will not be on the final. So lump capacitance will not be there. Yeah, everything's going to be steady state. Okay. Okay, radiation exchange. So this is the most recent topic that we've been covering. Okay, so radiation exchange, just in a nutshell, this pertains to kind of the exchange of heat between different surfaces via radiation. And so whenever you have, two surfaces or two objects that are kind of within relative close proximity, the assumption is that, they're going to be exchanging heat via radiation. Okay. Okay, so it looks something like this. So maybe we have, potato 1, potato number 2, right? Both of these objects are at a non-zero temperature. And, to be fair, every object of them is at a non-zero temperature. Okay. And so what's going to happen is that object 1 is going to be radiating outwards. Okay, object 2 is going to be radiating outwards. And they're going to be exchanging heat via radiation. Okay. So that's the situation. So, in the problem that you're going to see with this in the exam, you're going to have 2, 3, 4 objects, and they're all going to be radiating on each other. Okay. Now, with these problems, there's basically kind of a systematic way to kind of go through solving these problems. Okay. Step one. Step one is to draw the thermal circuit. Okay. And, just like we talked about on Tuesday, the thermal circuit for radiation problems is actually a very important step, because it's in this step that you basically lay out all the different pathways that heat can go. And with radiation, it's a lot more complex. And so you don't just have heat just going in one direction. Because radiation can go all different directions, you need to account for every single combination of different surfaces that can exchange heat in your situation. Okay. Okay. And so in the example that we're going to do, you're going to see that process kind of played out. Okay. Okay. Step two is to compute all the view factors. So the view factors, remember, these are the coefficients that we have, we call them Fij. Okay. So remember, view factors is the primary tool or the primary kind of method that we use to basically compute radiation between different surfaces. Okay. And the way that they're defined is that, the view factors basically tell you a percentage. Okay. The percentage of radiation that comes off of surface I that's going to impact or contact surface J. Okay. So remember, it's through these view factors that we basically simplify our calculations, because if you were to kind of analyze these radiation problems and you go from its governing equations, the geometry often becomes very, very difficult. So with the view factors, we're able to kind of simplify that and do things in a very kind of algebraic way. Okay. And the advantage of using view factors is that view factors have quite a few properties that we can take advantage of. Okay. And so the two that you're going to use the most are summation property and reciprocal property. Okay. And so oftentimes, when you look at a particular problem, you may be able to find 1 or 2 or 3 view factors just by inspection. And then by utilizing these other properties, you can compute all the other view factors within the problem. Okay, and then part three, once you have the view factors, you can then compute the radiation exchange. And so this part here depends on whether you have gray surfaces or not. Okay? And so if you have gray surfaces, you can compute all the radiosities. Okay. But if you have all black bodies in your radiation circuit, then you don't have to do this step. Okay. And then step 4, once you have the radiosities, is to compute any radiation exchange utilizing the circuit. Okay. All right, so that's the process. And so the thing with kind of the nature of the problems that we can do, you're basically going to follow this process for every single problem. So just like in our convection problems, we have that 5-step process to computing convection coefficients. For radiation exchange problems, we have kind of a 4-step process here. So definitely get familiar with this. You are definitely going to make use of this on the final exam. Okay, so let's do an example together. So let's go ahead and do the problem from the practice final. Okay. So in this problem here, we have basically 2 objects. Okay. We have a cylinder. Okay. And so cylinder has a particular diameter. So we'll call it D1. Okay. And we know the surface temperature. The surface temperature is going to be T1. Okay. Okay, so the setting for this is that this cylinder represents maybe a part of a space station or maybe part of a satellite that needs to be serviced. And so the other object that we have in this problem is we have a dude. Very technical. He's a happy dude. Okay. And so this dude here is an astronaut. Okay. And so he has a certain surface area. So we'll call this A2. He is at a certain temperature, T2. Okay. And this astronaut is going to be a gray body. So we're going to say it has a non-perfect emissivity. So we'll have E2 here, which is less than 1.0. Okay. Okay. So let's see. So we have some numbers here. So D1 here, this is 1.5 meters. T1 here is 400 Kelvin. We know the depth as well. So the cylinder is going to extend into the page by an amount of 1 meter. Okay. For our astronaut dude here, we have his surface area is going to be 1.95 meters square. His emissivity is going to be 0.65. Okay. And his temperature is 300 Kelvin. Okay. And also, because this space station is out in outer space, everything surrounding these 2 objects is going to be deep space. Right. And so if you want, you can draw a box around all of these. Right? Okay. So the box that surrounds all these objects is deep space. Deep space has a temperature of 0 Kelvin. Okay. So I'm going to use T infinity here. I know we've used T infinity for convection situations, but T infinity here is just the temperature of all the space that's surrounding. Okay. Okay. Additionally, we do have one of the view factors. Okay. So we are given, and let me write this in red. Okay. So the view factor between the cylinder and the astronaut, F12, is given as 0.3. Okay. Okay, and so in this problem, ultimately we want to compute. Running out of room here. Okay, ultimately, we want to compute the radiation heat loss to space from the cylinder and the astronaut. Okay, let me zoom out so you can kind of see the whole thing here. Okay, so that's our situation. So we have, two objects, but essentially we have a third object as well. So the third object, they're going to represent deep space. And we want to find out how much heat is being lost from the astronaut and from the cylinder to deep space. Okay, so this is a very standard radiation exchange problem. And so we are going to go through our 4-step process and compute everything. All right, any questions on this? Yes.
Given U factor, are we gonna be like on the test, are we gonna be like?
Yes.
From like which surface it is?
Yes, exactly. Yes.
So it'll be up to us to like what exactly what U factor is, like F1, 2 or F3.
So in the problem actually just tells you that, this is F12 is equal to 0.3.
Okay.
And I'll have all the surfaces labeled with the number, so you'll know exactly which two surfaces it's between. Yeah. Okay. All right. So let's go ahead and start the process for solving this. So first thing we need to do, we go back to our radiation exchange, process. We need to draw the thermal circuit for this problem. So let's start with that. Okay. Question, yes.
Did you mention whether or not the cylinder is a black or gray?
Oh, thank you. Yeah. So the cylinder is a black body. So we're going to assume that epsilon1 is equal to 1.0. Yeah. Thanks for catching it. Yes.
So for the area, is that the cross-sectional area of the circle or like the surface area?
This is surface area.
Okay.
Yeah. So I think the only one I gave you here was just the astronaut. So that's the surface area of the astronaut.
Okay.
Yeah.
That might be a little complicated to figure out ourselves.
Yeah.
Also for the cylinder, you have to find the surface area of the lateral and the circular.
Exactly. Yeah. Yeah. So we'll do that in a second. So for the cylinder, yeah, you would need the surface area of the lateral and the caps too. Okay, let's draw a thermal circuit. So the way you draw these thermal circuits is, you have to count how many objects that you have in the diagram, and you're going to make an end node for each one. Okay, so we have 3 objects here. So, we have astronaut, cylinder, and deep space, right? And so where the deep space is just whatever is surrounding these two. Okay, so let's just go ahead and make a node for each of them. Okay, so I have my 3 nodes here. We'll say the one on the bottom right here, that's going to represent the astronaut. The one on the bottom left, that's going to be the cylinder, number 2. And then the one up here, that's going to be deep space. Okay. And so for each of these end nodes, you're going to write out the total emissive power of that object. So that's going to be sigma T to the 4th power. So for node 2, we have sigma T2 to the 4th power. And up here, for deep space, we have sigma T infinity to the 4th power. Okay. Where I know T infinity is 0, but we'll just be explicit and write the whole thing. Okay. Next thing that we're going to do for your thermal circuit is that for every gray body in your in the situation, you're going to write down its gray body resistance. Okay. So our only gray body in this situation is going to be object 1, which is the astronaut. Okay, and so for the gray body, you're going to draw a resistor. Where this resistor represents the gray body resistance of object 1. So it's going to be 1 minus epsilon 1 divided by epsilon 1 A. Okay. Oh, did I switch the numbers? The astronaut is 2, huh? Okay.
Good question.
Yeah.
So after we do the surface resistance, then we would put that J node and then.
Exactly.
Okay.
Exactly. Yeah. So that's the next thing that you would do. Yeah. So I apologize, I mixed the numbers up. So object one in the diagram was a cylinder, but we'll say, just to be clear, this here represents the astronaut. Okay. Because remember, the cylinder is a black body, so we don't need to do this. Okay. So we have J1 for that astronaut. For all the other objects here, all other objects are black bodies, and so we don't need to draw a gray body resistance. Well, you can. It's just the gray body resistance is just going to be 0. Okay. All right, and then from here, what you're going to need to do is you're going to connect all the nodes to each other. Okay? And so that represents all the different ways that radiation can go. So if you look at the astronaut, right? Heat can go from the astronaut to the cylinder, and it can go from the astronaut to deep space. So this resistance right here, represents the heat transfer between the astronaut and the cylinder. Okay, so this is going to be R12. This is going to be 1 divided by A1 F12. Okay. And we have the heat transfer between the astronaut and deep space. So this is R1 infinity, which is equal to 1 over A1 F1 infinity. Okay. Right, and then we have one resistance that connects these two. So this is R2 infinity, 1 over A2 F2 infinity. Question, yes.
Wait, do you also have a surface resistance at all or no?
No, so for the cylinder, because its emissivity is 1, then we assume it's a black body. Exactly. Yeah. Mhm. Yep. Yes. So this J here, we include this J for every gray body that we have in the system. And so whenever you have a gray body, remember, a gray body is not a perfect emitter. It's not a perfect absorber. And so this J here represents not only the amount that's emitted from surface 1, but it also includes all the radiation that's reflected off of surface 1 as well.
Which one is surface 1 again? Is that the cylinder?
Surface 1 is the astronaut. So I mixed up the numbers, unfortunately. So
Oh,
yeah. I apologize for that. I looked in the bottom right. I thought, astronaut should be number 1. So, but yeah, so I apologize. I mixed up the numbers. Question, yes.
Speaking of 0.2, if it did have a surface resistance, will we just lock that with J and then extend another 0.5?
Exactly. Yeah. So if surface 2 had a surface resistance, you would basically, well, it would look like this. And so we change this to J2, and we have one more resistance here for the for that.
So only not the surface, but the other resistance are the only ones that really connect.
Exactly.
Okay.
Yeah. Yeah. Question, yes.
So your gray body is, your E is anything less than 1, right?
Exactly.
So if
Yes.
it's not given, should we assume that it's a black body?
Yes. So if it's not given, you can assume that it's 1. Yeah. Mhm. Yes.
So, since we mix the numbers up for R1 between 1 and J1, are we using epsilon 2 instead, or do you just leave it as epsilon 1?
Yeah, it should be epsilon 2. Actually, let me change the numbers back. I think that would make it a bit easier. Yeah, so these are all 2s right here. I apologize. I was like, should I keep going? Like, no, let's change. I was too stubborn to change. Okay, so this is node 2. This is node 1. There we go. This should be 2s right here. There we go. I think that's everything. Okay. Yeah, that should be it. I apologize. Yeah. Hopefully everyone caught all the switch. So I switched node 1, so it's on the bottom left, and then node 2 is on the bottom right. Yeah. Yes.
Sorry. So for the R12, would that change to R21 or like?
Oh, you could. But remember, because of the reciprocal rule, we have A1 F12 is equal to A2 F21. So you can use either one in that case.
But don't we want that intent for 2?
you can compute area one. So area one, you have, it's a cylinder, and so you can compute the surface area of the same. Mhm. Yeah, so it's up to you. So actually for this one, you're given A2, but you're also given F12. So usually it's a bit more difficult to find the view factor. So I would go with the view factor that you know. Yep. Mhm. All right. All right. Any other questions on the circuit here? Okay. All right. So now that we have our circuit, this one's not too bad. So, we just have three surfaces, just one gray body. So let's go ahead and compute all the view factors. Okay. So when the problem asks you to compute the view factors, even if it says to compute all the view factors, really the only ones that you need to compute are the ones that you need to complete the circuit. Because in reality, there's a lot of view factors that you can compute because every combination of different surfaces has a view factor, right? And so if you were to compute all of them, you would need F12, F1 infinity, F21, F2 infinity, then F infinity 1, F infinity 2, okay? So technically there are 6 view factors in this problem, but we only need 3 of them. And so if you look at our circuit here, right, we only have 3 internal resistances. And so if we highlight the view factors, we have F12, F1 infinity, and F2 infinity. Okay. So let's focus our computations on those. And so, we need this one, and this one. So we're not going to bother computing the other ones. You can if you want, but you only really need the ones that are needed to complete your circuit. Okay. Okay. All right, so let's go ahead and compute these view factors here. Okay. Now, actually, maybe I should step back. So you might need one of these other ones to apply the rules, but we only need to compute these 3 for the circuit itself. Okay. Okay, so let's start with F12. So F12 is already given to us. So F12 we already know from the problem was 0.3, I believe it was, right? Yeah. 0.3. So this was given. Okay. And you can expect that to be very similar to the exam too. So on the final exam, I'm going to give you at least 1 or 2 of the view factors, and so you can expect those to be given to you. Okay. But normally, if you're not given one, you would compute this using the table. But you're not going to need the view factor table for the exam. So don't bother writing that on your cheat sheet. Save yourself a bit of space. Okay. Okay. So that's one of them done already. Next one that's going to be easy for us to do is going to be F1 infinity. Okay. So the reason I'm starting with this one is that this is a view factor that involves surface 1, right? And we already have a view factor that's from surface 1 that was given to us. Okay. So that means what this tells us is that we're very likely to be able to compute this one using summation rule. Okay. Because if we sum up all the view factors that involve surface 1, they should all equal 1 because we're assuming that we have an enclosed situation here. Okay. So if we add up F11 plus F12 plus F1 infinity, okay, that should all equal to 1. Okay. Now we already know F12. F12 is right above this. So F12 we know is going to be 0.3. Okay. All right, F11, we already know as well, because if we look at the geometry for the cylinder, right? The cylinder is going to be radiating heat off its outer surface. And because the cylinder is a convex surface, it's impossible for the cylinder to radiate on itself. Okay. And so that just leaves us with one unknown in the problem, which is F1 infinity. Okay. And so this tells us that F1 infinity is equal to 1 minus 0.3, which is 0.7. All right, so that's the second view factor that we need for the problem. So the last one that we need is F2 infinity. That one's going to be a little bit trickier, but we're still going to use the same principles here. Okay. Any questions on how we got these view factors so far? Okay, good. Okay, so last one we have here is F2 infinity. So this one's going to be a little bit tricky because we don't have any of the view factors that relate surface to anything just yet. Okay, so it's going to be a little bit harder to apply the summation rule, but at the same time, let's go ahead and write out our summation rule anyway. Summation rule is probably going to be your most useful property that you're going to use, just because it's usually a good one to solve for these view factors. Okay. So our summation rule here, we're gonna involve all the view factors that involve surface 2. So that's gonna be F22 plus F21 plus F2 infinity is gonna equal to 1. Okay. Okay. So F2 infinity, that's the one that we want, and so we know that one's unknown at this point. Okay. So I think I forgot to say, I think it says in the problem that F22 here we can assume is 0 as well. Okay. Generally, unless the surface is very obviously can radiate on itself, most of the time you're going to assume that the self view factor is going to be 0. Okay. That's pretty reasonable. And so, if you do get a situation where self-irradiation is possible, the problem will probably tell you that that's the case. Okay. Okay. So that means the last view factor that we need to solve for in this problem is F21, okay, which we don't have, but we can actually solve for it. Because we may not have F21, but we do have F12. Okay, so we can compute this using F12. Okay, and the other view factor rule, which is the reciprocal rule. Right, because we know that F12 multiplied by A1 is equal to F21 multiplied by A2. Okay. Okay, and so if you solve for F21 here, so F21 is going to be A1 over A2 multiplied by F12. Okay. We have everything that we need for this problem here. Now, A1 is a little bit complicated to compute because this is the area of the cylinder. And so that surface area is we need to multiply the two surface areas of the caps. So it's going to be 2 pi d1 divided by 2 quantity squared. Okay. So that's the area of the caps. And then to that, you're going to need to add the area of the lateral surface. So that's pi times d1. And I believe the variable that we used for the depth into the page was little d. Okay. Okay. Good. All right, so I don't have the solution in front of me. I also only have my phone calculator right now, so just assume that you can compute this. Okay. Right. And so once you have A1, you're given A2, you're given F12. That means you can compute F21. The value for this should be pretty close to F12 actually, but I don't want to put any false numbers here, but you have all the numbers to compute this. I just don't have a very good calculator with me right now. So, okay. And so with this, we can compute F12, F21, which we can plug in up here. Okay. And then you can use that to compute F2 infinity using the summation rule. Okay. All right, question. So would you be given the surface area in the final, or should you put it on your formula sheet? So you should know the surface area of some common objects. So I would say cylinder, sphere, is you should know. So if that's something that you want to put on your cheat sheet, I definitely would do that. I wouldn't give you anything more exotic than a cylinder or a sphere though. So I would definitely be prepared for cylinder, sphere, and a flat plate. Yeah, I would definitely be prepared to know the surface area for these ones. Yeah.
What's the area that
So the surface area of the astronaut that was given, since the astronaut has a weird shape. So A2 is 1.95 meters squared. Yeah. Mhm. Yeah, so A2 you can just pull it straight from the problem, and then A1 you can compute from the area of a cylinder.
If anyone has calculated that view factor, it's because I'm getting a big number. I might be doing wrong.
It should be, it might be a little bit bigger than the than F12, but it should be should still be pretty reasonable. Well, okay, so let's see. So diameter is 1.5, right? So 1.5 divided by 2. I guess we're computing it. Okay. 2 pi, right? Okay, so that's going to be
You want to use my decimals calculator?
that's okay. Okay, so 1.5 divided by 2, that's 0.75 times 0.75 times 3.14 times 2. Okay, so this right here, this is 3.5325. Okay. And then the other one, we have 3.14 times diameter 1.5. So that's 4.71. Okay. Okay. And so we add these two together, 3.5325. So this is about 8.24 meters square. Okay, so that's the surface area of the cylinder. Okay, and then we're going to divide that by the area 2. So we're going to divide this by 1.95. Okay. And so this quantity right here, this is about 4.23. Okay. Okay, and so we multiply that by F12. So F12 was what? 0.3, I believe. Okay. So F12 here to 0.3. So that means F21, something greater than 1. I see the issue here. Okay. Okay. So if we're doing it with like this, F21 is equal to 1.27, which shouldn't be the case. So you should not get view factors greater than 1. I think what I did for this one is I neglected the surface area of the caps. And so I think that was probably in the problem that I forgot to mention. Okay, yeah, I'm sorry. So in the problem here, it says to neglect the surface area of the caps. And so that should help kind of bring down that surface area. Yeah.
After you ignore it, I get a value of 0.72.
Yeah, I think that's about right. So yeah. So all the view factors here should be less than 1. Yeah, so that's kind of one good sanity check that you can do for these problems is to make sure that they're less than 1. Okay. I apologize. I should have, yeah. The difficulties of reading reading a problem on your phone as you're doing it in real time. Okay. All right, so that gives you F21. So F21 here, that's about 0.72, I think you said. And then so that means F2 infinity is about 0.28 in this case. All right, any questions on this? Okay, good. Okay, so now that we have all the view factors, we can now compute the all the resistances in the circuit. Okay. So now we can compute R1 infinity, R12, and R1 infinity. Okay. Okay. So just in the interest of time, I do want to get to radial heat conduction. So I'll just kind of outline what you have to do for the rest of the problem. Okay. And so the last step in this problem is we want to compute the heat loss from our 2 objects to deep space. Okay. So deep space is surface infinity here. So that means we're going to compute Q1 infinity and Q2 infinity. Okay. Okay, so the way you're going to do this is that you're going to go back up to the circuit and you're going to compute the difference between the 2 nodal values on the inner part of the circuit, divide by the resistance in between them. Okay. So for instance, for surface 1, right? Surface 1 is our black body. And so the heat transfer from the cylinder to the environment is going to be going along this path right here. Okay. All right, so we need to compute the heat transfer along that path. And so that's going to be sigma T1 to the 4th minus sigma T infinity to the 4th divided by the resistance in between them, which is R1 infinity. Okay. And then similarly for surface 2. Now, surface 2 is a gray body. And so what we're going to do is we're going to subtract J2, right? So we have J2 minus sigma T infinity to the 4th divided by R2 infinity. Okay. Okay. And you have most of the numbers that you need for this one. The only one that you don't have is J2. Okay. And so before you can actually compute this, we need to compute J2. Okay. And J2, the way that we're going to compute this is we're going to use our nodal summation rule in our circuit. Okay. So this last one here is a few different steps. And so, first you need to compute the radiosity, then you're going to plug in the radiosity into this equation to compute the heat loss. Okay. Okay, so for the radiosities, let's go back up here. Okay. So this J2 node has 3 branches coming out. So we have 1 branch coming in and 2 branches going out into the middle of the circuit. Okay. Okay. So if we're going to do this, we have sigma T2 to the 4th minus J2 divided by R2. Okay. So this is the heat coming into node 2. Okay. And then to this, we're going to set this equal to all the heat that's leaving the J2 node. So it's going to be J2 minus T 1 the 4th times sigma divided by R12 plus J2 minus sigma T infinity to the 4th divided by R2 infinity. Okay, because with this equation right here, we have, even though it's a lot of terms, we actually have the values for everything here except for J2. So you're going to use this equation to solve for J2, and then plug that J2 into this equation to solve for Q2 infinity. All right, I know that was kind of rushed, but hopefully with at least with the equations here, you have everything you need to go and plug it in. All right, any questions on this last step here? Yes.
With other circuits that we've seen so far in the class and homework doing that, is that as difficult as the field can?
You might see an additional surface on the exam. So this circuit here has 3 surfaces. There's only so much creativity I can do with 3 surfaces, so you might see a 4th. But I would give you more view factors in that case to kind of simplify the calculations. Yeah. And with more surfaces, that's more view factor calculations. I probably wouldn't have you do something as complex as this last step. Maybe I just have you solve for the radiosities in that one.
Okay.
Yeah. Question, yes.
So on the study guide, how it says like solve for gray surface or gray body and black body, is
Yep.
this exactly what you're talking about?
Exactly. Yeah. So this has both gray body and black body radiation exchange.
I know on the notes, there's a lot more complex equations, so I didn't know if we were also doing that or just this.
Just this. Yeah. Yeah. So just the circuit stuff. So I know we went on a sidetrack with like solid angles, stuff like that. You may see a conceptual question from that area, but not the problem is going to look very similar to this.
And when you, just to clarify, when you say radiosities, it's basically the resistance of that circuit, right?
So the radiosity is actually the nodal value. So radiosity is actually this J2 right here.
I see.
So the resistance is something different. The resistance is there. But the radiosity is actually the nodal value that's just past that resistance.
And then I remember last lecture you said you'd most likely just have us set it up.
Exactly.
Okay.
Yeah. Yeah. If it's more than one equation to solve for the radiosities, that takes too long to solve in practice. So I would just have you guys just set it.
Thank you.
All right. Any other questions on this problem here? Okay. But yeah, so for these problems, I would definitely focus on drawing your thermal circuits, computing the view factors. And for the last part here, at least know how to set up these equations. And I think you'll be good to go on these types of problems. Okay. All right. So for the second half of class today, I did want to talk about radial systems a bit. So, kind of really shifting gears here. Okay, so this takes us kind of all the way back to, I think, week 3 or 4 of the semester. So this is conduction in radial systems. Okay. Okay, so by radial systems, we have 2 types of radial systems. So basically we have cylinders and spheres. Okay. And if you recall, from the first midterm, there are broadly kind of 2 categories of problems that come out from this part here. So on the one hand, we have heat equation type problems. Okay. So with heat equation type problems, that in those problems, you're going to be solving a differential equation. Okay. And so you're going to be solving for the temperature distribution in a cylinder or sphere. Okay. So that involves starting from the full heat equation, canceling terms through to assumptions, applying boundary conditions, integrating. Okay. So that's a big part of it. The other type of problem that we have in these from this unit is thermal circuit type problems. Now, these are kind of the OG thermal circuits. So these are the thermal circuits that only go in one direction. Okay? So these thermal circuits, would look something like this. Okay. Now, for these thermal circuits, what I'm mostly interested in is, first of all, can you, at least represent all of the resistances in the circuit? And you're going to need to compute all of the resistances as well. Okay. Okay, so if you go back, to our first midterm, you can look at the practice midterm for the first midterm. That would be definitely good to check out as well. You'll see that all the problems kind of fall into one of these two categories. Okay. Okay, so let's see. So we can kind of make a choice here. My feeling is that, I think, probably be better to review the heat equation type problems. And then, if we have time, we'll go over the thermal circuit type problems as well. But just know that there's kind of two paths here. But, for now, let's just focus on this one. Okay. Okay, so for these heat equation problems, the process through which you solve them is kind of the same. Right? I don't know if I've ever written down kind of a step-by-step process for these problems, but I think now is as good a time as any. Okay. Okay, so the first step to solving these heat equation type problems is to start. So usually you're going to start from the full heat equation. Right, so that means starting from the full partial differential equation that represents the temperature distribution in your object. Okay. Now there are a couple forms of this, and so remember there's a form for cylindrical coordinates and a form for spherical coordinates. Okay. Let me try to pull up the spherical one. Way back here. Okay. So for the cylinder, so the full heat equation in cylindrical coordinates looks like the following. So 1 over R partial R times K R partial T partial R plus 1 over R squared partial theta K partial T partial theta plus partial Z K partial T partial Z plus Q dot is equal to rho CP partial T partial T. Okay. Okay. So that is an equation I would definitely have on your note sheet. Okay. As well as the spherical one. So for spherical coordinates, I'll give myself a little bit more room. Okay. So for spherical coordinates, it looks like the following. So we have 1 over R squared partial R K R squared partial T partial R plus 1 over R squared sine squared theta partial phi of K partial T partial phi plus 1 over R squared sine theta partial theta K sine theta partial T partial R or partial theta, excuse me, plus Q dot is equal to rho CP partial T partial T. Okay. Now, these look intimidating, I know, but remember, we're not actually solving the whole thing because, we're going to cancel out a lot of these terms due to our assumptions. Okay. But it's good to start from the whole thing just so that kind of, when you list out your assumptions, what terms you're going to cancel and why you're going to cancel them. Okay. So yeah, these equations I would definitely have in your notes. Okay. Okay. Step two in these problems is to state your assumptions. Okay. And so every time you solve one of these problems, you are going to have some assumptions, okay? You need to, otherwise, it would be impossible to solve these types of problems. Okay. So you're going to state your assumptions and cancel the terms from the heat equation. Okay. So let me list out some common assumptions that you're going to make. Okay. So the first assumption is steady state. Okay. So steady state is something that you're going to assume basically for the entire exam. We did do transient conduction for a little bit in this class, but that's not something that's going to be on the final. And so basically you can assume that everything here is steady state. Okay. So under the steady state assumption, any derivatives with respect to time is going to be equal to 0. So partial t is going to be equal to 0. Okay. Okay. And so if you look at our two heat equations here, so we have one for the cylinder and one's for the sphere. So we have a time derivative term in both. Okay. And so you're going to cross out these two terms here for the steady state assumption. Okay, so that's always the first assumption that you're going to make. Okay. All right, so the second assumption, I'm going to lump together a couple assumptions together, just because they all kind of have the same effect. So for the second assumption, we're going to assume that our heat transfer only occurs in the radial direction. All right, and so this assumption here has a few consequences, and so basically, what we're gonna say is that or our temperature does not depend on any variable except for R. So any derivative that involves any of the other variables. So we have quite a few here. So we have derivative with respect to theta, derivative with respect to z, derivative with respect to phi. All of those are going to be equal to 0. So partial theta is equal to partial phi. It's equal to partial z. All of those are going to be equal to 0. Okay, so let's go ahead and cancel all those terms in our equation up here. Okay. So we have this equation here. We're going to cancel that one out because we have a derivative with respect to theta. We have this term right here, which is a derivative with respect to z. This term right here, which is a derivative with respect to phi. And this term right here, which is a derivative with respect to theta. Okay. So everything that I've canceled in purple right there are all due to the 1D assumption. Okay, so that's going to simplify things quite a bit for us. Okay. Okay. So assumption A, assumption B, you're going to assume those basically for every single problem. And so, it'll be good just to kind of list those out. Assumption C here is something that we only assume some of the time. Okay. And so assumption C here is based on the thermal generation. Okay. And so in those situations, you're going to set the generation term, which is Q dot equal to 0. Okay. Now, usually, for these problems, the problem will tell you explicitly if there is thermal generation. And so if the problem does not say anything, you can usually assume that there's no generation in those cases. Usually, if there is thermal generation, it'll be stated in the problem, because that's usually the more unusual case, but most materials are not going to be producing heat, and so you can assume that the generation in those cases is equal to 0. Okay. Okay. And so if we go back to our equations here, we do have Q dot. So you have Q dot here, Q dot here. Okay. All right. And so if there's no generation, then you can assume that those are 0. Okay. Okay, so step 1 to solving our heat equations is just write down the whole heat equation. Step 2, state all of your assumptions and cancel your terms. You're going to end up, most of the terms are going to end up canceling. And so the only terms that should be left are going to be the terms that involve derivatives with respect to R. Okay. All right, any questions on this so far? Okay. All right, so step 3. So once you have your heat equation and after you've simplified it with your assumptions, the next step is going to be this to state the boundary conditions for your problem. Okay. Now, we're not going to apply these boundary conditions just yet. And so, the boundary conditions is something that you apply near the end. But before you start integrating and before you start solving for the temperature, it's always good to state what the boundary conditions are. Okay. Now, for radial problems, the boundary conditions, the way that you state them is, you kind of have to ask yourself what is happening at the inner radius of our problem and what's happening at the outer radius of the problem. Okay. And so for boundary conditions, you have kind of 3 possibilities here. And so, to choose the right boundary conditions, you guys need to look at the figure that's given to you in the problem and also read the text, because, these, which of these 3 conditions that you choose is going to depend on what the problem is stating. Okay, so generally your 3 possibilities for boundary conditions are: 1 is a specified temperature. So for a specified temperature, we have T of R I is equal to T naught, or given. Okay. Maybe I shouldn't use T R I here. So maybe this is T R R given, I guess it's RG. Okay. Because it's not always the inner radius, but for cases we have a specified temperature, that's what you would do. Okay. Okay, second option is that you may have a specified heat flux. Okay. And so in those cases, you're going to use Fourier's law. And so that's going to be K times A partial T partial R at some radius is given to Q. Okay. Okay, and then the third option that you may have is what's called a convection boundary condition. And so in those situations, you have basically conduction heat flux. So Ka times partial T partial R at R is equal to Rg is equal to H times A T of Rg minus T infinity. Okay. Okay, so each of these three conditions here are going to present kind of different mathematical, ways that you're going to apply them later on. But you need to be able to kind of recognize from the figure, from the problem, which ones you're going to specify. Okay, so for example, right? So let's say that we have a generic cylinder here, right? We have a cylinder, right? We have an inner radius, Ri, outer radius, Ro, okay? And let's say that our boundary conditions look like the following. So, okay, so let's say that at Ri, right? The temperature at the inner radius of the cylinder is given as Ti, okay? And then on the outside of the cylinder, let's say that we have convection that's going on. Okay? So this is H, T, infinity. Okay. And so for this situation right here, your boundary conditions, you're gonna state the boundary condition at Ri and the boundary condition at Ro. Okay. So if it helps, I would definitely write out in words what these boundary conditions are stating before you go into the mathematics. Okay? Okay, so first we have the boundary condition at Ri. So at R is equal to Ri. Okay. And so we need to look at, at the inner radius of the cylinder, what is the thermal condition there, right? So at the inner radius, we have a specified temperature since we know what the temperature is at that interface. Okay. All right, so based on the figure, we know that the temperature there is Ti. Okay. And so that tells us that, we are the type of boundary condition that we have is a specified temperature boundary condition. So we have T at Ri is equal to Ti in this case. Okay. Okay. And so that's the first boundary condition in that we're going to use for this problem. Okay. At the outer radius here, we can see that the outer surface of the cylinder is being cooled by convection, or there's convection going on the outside. And so that means the type of boundary condition that we're going to apply at the outer radius is going to be a convection boundary condition. Okay, so in that case, we have minus K times the surface area. Where surface area we know for this case is 2 pi times RO times the length. Okay. Multiplied by partial T, partial R, evaluated at R is equal to RO. Okay. This is equal to H times A times T at RO minus T infinity. Okay. Where this area here is exactly the same. So that it actually ends up canceling out. So we have 2 pi RO L. Okay. So this part here is really crucial. And so, even if you integrate the heat equation correctly, if you apply the wrong boundary conditions, you're going to get a completely different answer. So this step is really crucial in these problems is to, look at the problem, look at the figure that's given to you, look at the problem, statement, and then from there, you can determine what type of boundary condition that you can apply. Okay. All right, because for every problem, it's going to be different. Okay. So make sure that you get the boundary conditions correct for these types of problems. All right, any questions on the boundary conditions?
You know, for some of them, the condition where it's like K R squared or something like that.
Mhm.
Are you able to take that out of the derivative form and just divide it away eventually, or do you have to take the integral and then do it?
So for K is interesting. So K is just a constant in these cases.
Okay,
And so for a constant, the constant does not depend on R. So you can actually take the K out and then divide by the whole thing.
okay.
That's fine. But because the radius here, the R, it's a function of R. So R is a function of R. So that one you cannot take out. Yeah. Mhm. Yeah, good question. Mhm. All right, so now that we have our heat equation in its final form, we have the boundary conditions. Next step finally is to integrate our heat equation. Okay. And so the heat equation is always going to be a second order equation, and so you're going to be integrating twice. Okay. Okay. You may have to do a little bit of algebra in between the intervals just because of the nature of the equations. Okay. And so after you integrate your heat equation, you're going to get some function T of R. And so your expression here for T of R is going to include some terms that depend on R. And the most important thing is that, remember, every time you integrate, we're doing an indefinite integral. And so your integral here is going to end up with two arbitrary constants. You're going to have a C1 term, which is usually going to have some function of R. It's either going to be C1 divided by R, C1 natural log of R, and a C2 term that's almost always going to be a constant. Okay. But C1 and C2 here are unknown constants, or they're arbitrary at this point. Okay. But just make sure you get those C1 and C2 terms, because that's kind of where most of the money is at for these problems. Okay. Because the last step that you need to do for these problems, okay, after you've integrated twice and after you get your C1, C2 terms, step 5 here is to mathematically apply your boundary conditions, and that will give you the equations you need to solve for C1 and C2. Okay. And so in all honesty, step 5 is probably where you're going to spend most of the time on these problems, because, it's a lot of algebra. It's especially if you have convection boundary conditions, heat flux boundary conditions, it can be a chore to solve for C1 and C2. Okay, so unfortunately, we didn't have time to do a full example of this one, but there's lots of examples like this in the notes, in the practice exams, in the homework problem. So make sure you guys are practicing these ones, especially step 3. So I remember from midterm 1, step 3 seems to be the one that a lot of people struggle with. So recognizing the boundary conditions and writing them down is going to be key. Okay. All right. Any final questions before we wrap it up? All right, so since this is our last time, I just want to say, last question. How many problems will there be on the midterm? There'll be 3 problem-solving problems and 8 conceptual problems.
So for
Yeah. Yeah.
Can you do what Troy asks?
What?
Can you take that part for him?
He's always asking that. All right, so since this is the last time today, guys, I just want to say thank you again for a great semester. You guys have been incredible. I mean, this is probably the most engaged and wonderful heat transfer has been for me. So just want to thank you guys for a great semester. Looking forward to see you guys all next week. And I know a lot of you guys are graduating too, so I will see you guys all commencement too. So thank you guys. I'll see you guys next week and, yeah, have a good summer.
See you next year.
Yeah.
Okay, so we had, a heat exchanger. The Reynolds number for the water, which is continuous.
Yep. Mhm.
And we found that to be turbulent. Oh, I'm sorry. When it's laminar, do we have to make it either an assumption that it's.
Yeah, you do. Yeah, so, for most cases, you're probably assuming the process. That's just the class, that's just. And now for this class, you know, I'll tell you, which is. Yeah, for laminar flow, you have to choose, and that's what I tell you.
Okay, so like if we were to come across an example like this, I'm gonna sound. Okay. And I'm assuming you're giving us that assumption, you're telling us what's specifically gets to the.
Yeah.
But there are ways to actually.
Oh, yeah, yeah. So I mean, most cases are gonna be kind of in between. So there's never gonna be a case where it's wants to keep the floods. There's never gonna be. So it's always gonna be in between, but usually make the most difference. So I would say probably most more commonly it's gonna be as long as it's extent. Just based on my own experience.
Another question I have is, is it possible to get a negative rain?
It's not. So if it's a negative, then you probably have the temperature difference. And so you should swap the temperature.
Because I think I remember talking to you about it,
Yeah.
just take the absolute value.
Exactly, yeah.
Okay, thank you.
Yep. Yep. Yes, yeah, so not in their entirety, so I would definitely look at the study guide, so I did trim quite a few. Yeah, so like transient conduction is not gonna be there, DINS is not gonna be there, reconvection heat exchangers, I think I trimmed all of them, I think maybe a couple more. Yeah, definitely look at the stuff. Yeah. It's always two.
It's always.
I always do.
So just like, for like.
Yes, yeah, because heat equation is a second order differential equation, so you need two boundary.
And then. Like, I know what this is, like, convection,
Yeah.
but is this just like.
So this, on this left side, that's Fourier law, so that's basically our equation for conduction. And so this boundary, condition basically says that the heat that's leaving from conduction has to be equal to the heat that's leaving from convection. Conduction equal to convection.
Okay, okay. So this is the conduction part, this is convection.
Exactly.
Okay, for sure. Alright.
Yeah. Is it- what's up?
I wanted to bug you if I could get my exam.
Oh, yeah, yeah, just call me back to my office. Yeah.
This is, I was definitely starting.
Sure, yeah.
You'll be uploading, not today's lecture, but, next.
Yeah, yeah, I forgot to upload
Yeah.
Tuesday, so I'll upload both today.
Okay.
Yeah.
Thank you.
Mhm.